So we're here to celebrate the Morgenstern Award and the winner of the award this year. And a little bit first about the award. The GSE introduced what was then called the GSE Graduate Student Award in 1989. That was renamed as the Morgenstern Student Award in 1999. The award is given to the graduate student who submits the best paper as selected by the professors in the Geotechnical Division of the Department of Civil and Environmental Engineering at the University of Alberta. Along with the monetary award and a certificate, the award winners are invited to present their paper to the general membership. This year, this important event takes place online. Might even be the first time that's been done. So keep that in your memory, Amir. So our award winner this year is Amir Haghi, PhD. His lecture will be on Geomechanical Controls on Multiphase Fluid Flow in Naturally Fractured Carbonate Reservoirs. He's currently a postdoctoral fellow with the Reservoir Geomechanics Research Group at the University of Alberta. His primary research interests include geomechanics and multiphase fluid flow in earth materials for applications in subsurface CO2 storage and the wider geoenergy field, such as geothermal energy and hydrocarbon recovery. Amir received his PhD degree in geotechnical engineering, reservoir mechanics, in January of this year from the University of Alberta, under the supervision of Dr. Chalaturnyk and co-supervision of Dr. Sebastian Geiger at Heriot-Watt University in the UK. And Rick is with us tonight, or this afternoon, so thanks very much for joining us, Rick, and I'm sure there'll be plenty of questions. Amir will be presenting today a lecture on novel semi-analytical model. It was a novel semi-analytical model that he developed to study the influence of stress-dependent effects on porosity, absolute permeability, and relative permeability, and the effects of capillary pressure on the imbibition and oil recovery mechanisms of both intact rock and fracture in a cubic block model. To capture geomechanical interactions involved, pure compliance poroelastic definitions and nonlinear joint normal stiffness equations were used to assess the deformation of intact rock and fracture respectively. Amir, the virtual floor is yours.
Okay, thank you, Sean. Thank you very much. Let me share my screen. All right. Thank you very much. My presentation today, which is mainly the main results from my PhD study at University of Alberta, is actually on geomechanical controls on multiphase fluid flow in naturally fractured carbonate reservoir. Yeah, this is the outline of this presentation. First, I'm gonna start with an introduction, problem statement. Well, there are two main questions associated with this research. The first is where the idea of stress-dependent multiphase flow comes from, and the second one is why is it so important? To answer these questions in this slide, I'm gonna explain schematically the process of pore scale stress-dependent drainage imbibition. Just imagine that this box represents a porous media, and the circles are pores, which are initially 100% saturated with the wetting phase, which could be water. And this plot is showing capillary pressure versus saturation of these porous media. Now, by starting the drainage process, by injecting the non-wetting phase into this porous media, the first pore which gonna be filled with the non-wetting phase will be pore number 1, because it's the biggest pore in the porous media. And that's here you can see the capillary entry pressure. And then pore number 2, 3, 4, 5, and finally pore number 6. But as you can see, non-wetting phase here in pore number 6 is discontinuous, which is because of the size of the pore throat, and which we call it non-wetting phase trapped in this pore number 6. Now reversing the process for imbibition by injecting the wetting phase, The first pore which gonna be refilled with the wetting phase will be pore number 5, which is the smallest pore here. And then 4, 3, 2, and 1. Now imagine that due to reservoir depletion in this porous media, effective stresses decreases, pore pressure decreases. That's why effective stress increases on this porous media, which cause pore size decrease. Now, repeating the process, drainage and imbibition process in this deformed porous media, similarly, the first pore which gonna be filled with the non-wetting phase will be pore number 1, the biggest pore. But as you can see, the size of that is smaller than the initial size of the pore. That's why capillary entry pressure will be higher than the initial value. And then 2, 3, 4, finally pore 5 and 6 trapped, and reversing the process for the imbibition, injecting the wetting phase, 4, 3, 2, and 1. Here you can see that by changing the stress, capillary pressure curve and irreducible wetting phase saturation actually are changing, and this change has some major effects on multiphase flow, reserve, and recovery of a porous media. And as long as we know, these are the most important parameters for all industries who are dealing with multiphase flow in earth materials, or let's say geomaterials in the world, like oil and gas industry, CCS, or geothermal reservoirs, and etc. Now the question is that should we expect the same process in a real porous media with a real multiphase flow or not? Objective and scientific hypothesis of my research. Here I investigated, in that research, I investigated stress dependency of intrinsic rock properties. As we know that porosity and absolute permeability, we are expecting them to decrease by increasing the effective confining stress. And stress dependency of multiphase flow properties, for instance, for an initially water-wet rock with this relative permeability and capillary pressure curve, based on the rationale that I presented in a previous slide, be expecting by increasing the effective confining stress, relative permeability curve shifts to the left, and capillary pressure curve shifts upward in this way, and irreducible wetting phase decreases. For an initially mixed wet rock with these curves, we are expecting increasing the effective confining stress, relative permeability shifts to the right, and capillary pressure shifts upward in this way. And finally, the last objective was stress dependency of recovery of multiphase flow mechanism, which based on these change that I explained about intrinsic and multiphase flow properties by stress, we are expecting that the recovery of multiphase flow mechanism also affected by stress like this. Okay, methodology and result of this study. I classified this research into 4 main sections. The first main section was field scale geomechanical investigation, which I studied Morgenstern Natural Fractured Carbonate Reservoir in southwest of Iran here. And in this study, I measured orientation of maximum horizontal stresses using image log analysis and magnitude of vertical stress, a minimum horizontal stress, and maximum horizontal stress using a wide range of data and methodologies, including using density log, extended leak-off test, step rate, hydraulic fracturing, acid fracturing, and a formulation that I introduced and call it deformation diffusion thermal approach. And using actually these stress states, we define the stress regime in that field as a normal stress regime. And finally, 1D mechanical earth model using dipole sonic image logs. Here you can see compressional and shear wave velocity, and then calculating the elastic modulus, Poisson's ratio, and strengths for the whole thickness of the reservoir, which was almost 1,000 meters. And the results have been published in 2018 in International Journal of Rock Mechanics and Mining Sciences. The second main section was analytical solution. In this study, I investigated stress-dependent spontaneous imbibition in a fractured porous cube like this. And actually, we developed a flow diffusivity equation for flow into this dual medium box of porous media. And but this actually flow diffusivity equation was different from the classical flow diffusivity equation in the literature, as porosity is no longer a constant, it is changing with stress. And finally, capillary diffusion coefficient is also a function of effective stress. And this is actually this showing the workflow for the analytical solution, changing the stress. The model starts to calculate stress-dependent porosity, absolute permeability, capillary pressure, and relative permeability for each medium matrix and the fractures, and then using some valid mixing rules and equivalent continuum concepts. The model calculates the property for the whole media, fracture and matrix. And the results goes into the solution of this partial differential equation. And then we got some ideas about stress-dependent spontaneous imbibition. And actually, this study have been published in 2018 in Water Resources Research. Here in this slide, I presented some of the analytical results by comparing two different scenarios with geomechanical control, scenario number 1, and without geomechanical control, scenario number 2. This is showing the porosity for comparing two different scenarios, and this is the absolute permeability with geomechanical controls and without geomechanical controls. These two plots are showing capillary pressure and relative permeability for scenario 1. You can see that they are changing with the stress or with time, but for scenario 2, it's just a single line. There is no stress sensitivity. And then finally, oil recovery versus effective stress versus time, comparing two different scenarios, scenario 2 and scenario 1. And we calculated almost 50% drop in the recovery of the block of matrix by adding the impacts of stress-dependent intrinsic porosity and absolute permeability and multi-phase flow properties into the model, which was kind of novel study at that time. And the third main section of this study was numerical modeling. Block to fill a scale approach using CMG GEM. As you can see, the modeling was in two different scales, a block scale and reservoir scale. We first initially developed a fine grid block scale model to investigate stress dependency of spontaneous imbibition in a single porosity model. It was single porosity because we assigned fracture properties to the fracture grids and matrix properties to the matrix grid, but it helps us to simulate this classical sugar cube array of Varnon roots original dual porosity model. And this plot is showing matrix black hole recovery with time at 10 MPa effective confining stress, and then increasing the effective confining stress to 30 MPa, we calculate a 30% drop in the matrix black hole recovery in this model. And for the field scale or reservoir scale model, actually we developed a fine grid reservoir scale model to investigate impacts of geomechanics in a coupled dual perm 5-spot model, 4 injector at the corners, 1 producer at the center. And in this plot, you can see the reservoir pressure decline up to this time due to the reservoir depletion. And at this moment, after 1 year, water flooding starts in the model. That's why the pressure goes up and then becomes plateau. And this plot is comparing cumulative oil production from this model, comparing two different scenarios. The solid blue line is the conventional simulation. There is no geomechanics inside this model. And the colored one is the coupled actually geomechanics and flow simulation by adding the impacts of stress-dependent intrinsic and multi-phase flow properties in a sequential manner. And here you can see that we calculated 40% drop in the oil recovery by adding all these impacts, and we presented this study in an EAG conference in Oman in 2018. And the last main section of this study was experimental approach. Here in this part, I conducted some experiments in two different scales, core scale and pore scale. For the core scale experiments, this is the equipment that I upgraded in the GeoRef lab, which consists of 3 main units. Confining pressure circuits, which gave us the opportunity to apply a wide range of effective confining stress on the specimen. Pore pressure circuit, which gave us the option to run 2-phase core flooding experiments, and finally gas separation unit that collected the whole phases from the specimen, separate them, and the data used to measure to calculate the saturation of the specimen at each stress condition. And using this equipment, I actually investigated porosity by measuring change in the pore volume, absolute permeability using steady state water injection, relative permeability using modified Hassler method with water and nitrogen phases, and capillary pressure using modified stationary liquid method with water and nitrogen phases. And afterward, in pore scale, we have done some micro scale pore visualization and analysis using micro CT. And then this 3D model of the pore space actually used for an approach that we called it stress-dependent pore flow modeling, which consists of conceptual proxy modeling approach, which actually deformed the pore space because of the stress, and then adjusting the deformed pore space with the pore strain from the experimental core scale experimental data. And the results of this deformed pore space goes into this workflow. Conceptual proxy model goes into this workflow, which consists of extracting a pore network model for the deformed pore space, and then modeling the fluid flow into the deformed pore space. Here, I'm gonna first present some of our core scale experimental results. The first specimen which was tested was Berea sandstone, homogeneous intact specimen, water wet rock. This plot is showing stress-dependent porosity and absolute permeability by increasing effective confining stress from 0 to 30 MPa of the specimen. This plot is showing relative permeability of the specimen. Actually, this one is from the literature with no stress effect. By increasing to 10, 20, and 30 MPa, we observed a leftward shifts in the relative permeability curve of the specimen, which is in agreement with initial hypothesis of this research. And in terms of capillary pressure, increasing it to 10, 20, and 30 MPa, we observe an upward shift in the capillary pressure. And the result of this study have been published in 2020 in Water Resources Research. The second specimen which was tested was a calumet carbonate, a heterogeneous intact specimen, which was coming from McMurray downburden formation from Alberta, Canada. As you can see visually, it's a heterogeneous rock, different mineralogies at different parts. And even the contact angle of these different mineralogies was different. That's why we concluded that this rock is a mixed wet rock. And once we have water and air, and in case of water and oil, we actually recognize the rock as an oil wet rock. And this plot is showing UCS test results of the specimen, which gave us a UCS almost 36 MPa, which is big. And the elastic modulus, Young modulus of 3 GPa shows that it's a very stiff rock. And permeability and porosity by increasing the effective confining stress from 0, here the blue, to 30 MPa red, we observe a decline in both properties. And you can see that the permeability of the specimen is in the range of microdarcy, which shows that the rock is almost impermeable. Then afterward, in the second part of this study, I induced actually an artificial fracture into the specimen and tried to characterize the hydrodynamic properties of the fracture in this rock, because the matrix was pretty much impermeable. This plot is showing stress-dependent absolute permeability and porosity of the specimen, and by increasing the effective confining stress from 0 to 10 MPa. And this plot is showing the experimental results. The black circles actually are the experimental results of the fracture actually closure with effective stress during loading and unloading. And I matched the Barton and Bandy's nonlinear joint model and the experimental data, which match greatly well. And this plot is showing relative permeability of the fracture at 1 MPa, increasing it to 5 and 10 MPa. We observed a rightward shift in the relative permeability, which is again in agreement with the initial hypothesis for a mixed wet rock. And during the unloading down to 3 MPa, a leftward shifts. And for the capillary pressure at 1 MPa, increasing it to 5 MPa, we observed actually great upward shifts in the capillary pressure. But this is not all. At 10 MPa, even a bigger or greater upward shifts in the capillary pressure, which shows that how fracture capillary pressure is sensitive with stress. And In the next experiment, the last specimen that I've tested was Indiana limestone, a heterogeneous intact specimen, which was a water-wet rock. And these plots are showing stress-dependent relative permeability and capillary pressure curves, which is similar to Berea sandstone, same actually shifts in the curves. And then actually we start to investigate the problem in pore size. This plot is showing stress-dependent pore size distribution of the specimen. At gray is the 0 MPa effective stress, and red is at 30 MPa effective stress. And you can see there is a leftward shift in the pore size distribution of the specimen. Pores becomes even smaller and shrink a little bit. And to actually investigate the physical mechanisms behind all these shifts in irreducible wetting phase saturation, we scanned this specimen here. And then in this plot, you can see I magnified a pore from the pore space here in this frame, and then zooming into this specific area of the pore, you can see a channel which is connecting a main pore to a branch pore at 0 MPa effective confining stress. And this plot is showing a capillary pressure versus channel radius, which I called it phase redistribution plot. Now, just looking into this channel, increasing the effective confining stress to 10 MPa, you can clearly see the channel deformed and compacted, shrink a little bit. And on this plot, the channel at 0 MPa was at point number 1. Now seeing at, increasing it to 10 MPa, we jump to point number 2. And we pass the onset of water capillary saturation. That explains that by increasing the effective stress, the viscous forces is increasing. That's why the gas can pass the channels right now and the water extracted from the pore. Increasing it to 20 MPa, you can see the channel becomes even narrower, and we jump to point number 3 on the plot. And finally to 30 MPa, you can see how the channel is compacting and closing. And we jumped on point number 4 on the plot. And this actually explains why the reducible wetting phase saturation of the specimens are decreasing or increasing by changing the effective confining stress. And the results of this study have been published in 2019 in scientific reports from Nature Research. And finally, the last experiment was same specimen, Indiana limestone. This plot is showing stress-dependent spontaneous imbibition recovery. We want to know how recovery is affected by stress. At 1 MPa, the blue circles, to 30 MPa, the red circles, we observed great downward shifts in the recovery of the specimen by increasing the effective confining stress from 1 MPa to 30 MPa. But we also investigated this problem into a pore scale. Here in this actually model, you can see at 1 MPa and 30 MPa, the simulations of the flow inside the pore space. And then using the results of these simulations and some analytical methods, actually we simulate the recovery of the specimen by changing the effective confining stress, and the results of the simulation matched with the experimental core scale results pretty well. And this study was a collaborative research with between us, Dr. Martin Blunt from Imperial College of London, UK, and Dr. Sebastian Geiger from Heriot-Watt University, Scotland. And we appreciate all their actually collaborations much. Here you can actually see in these two, comparing these two simulations visually, this part of the porous media actually becomes isolated and separated from the pore space. And that explains actually why change in effective stress in micro scale leads to some change in the in continuum scales in the irreducible wetting phase saturation. And the paper actually is under in review right now. We submitted 2 scientific reports. Okay, summary. In this research, I actually designed a study to actually containing analytical, numerical, and experimental approach to investigate geomechanical controls and multiphase flow properties in a number of sedimentary porous rocks and in an induced fracture rock. And our field scale actually approach shows the first full stress tensor of the field and 1D mechanical earth model of the Morgenstern Reservoir. And it revealed a normal fault stress regime in the field. Then applying some semi-analytical and coupled numerical techniques, we revealed some significant downward shift in the recovery of natural fractured carbonate reservoir in response to stress-dependent change in the intact rock and fracture. And we use X-ray computed microtomography and introduce a stress-dependent pore flow modeling approach. And using these methods, we revealed some increase in effective stress, which leads to some leftward shift in pore size distribution, closure of microchannels, and increase in flow path tortuosity for an Indiana limestone specimen. And finally, for the core scale experiments, we show that increasing the effective confining stress actually leads to some nonlinear decrease in the porosity and absolute permeability of all specimens. Leftward shift in irreducible wet in phase saturation of initially water wet rocks like Berea sandstone and Indiana limestone, and rightward shifts in a mixed wet rock, which was columnate carbonate, which was a fracture carbonate, and finally an upward shifts in the capillary pressure curves in response to an increase in effective stress. Okay, now I'm done with the presentation, but here I would like to express my gratitude to my supervisor, Dr. Chalaturnyk, Reservoir Geomechanics Research Group, and University of Alberta Geotechnical Center for all their supports during the course of my PhD and later on. And additionally, all financial supports from our industry sponsors. Here, you can see the name of them. During the last 4 or 5 years of my research at the University of Alberta, actually, I really appreciate it. And I would like to express that I'm extremely honored and privileged to be recognized as the winner of 2020 NR Morgenstern Award. What a name, and it's a big honor. And I'm deeply grateful to Geotechnical Society of Edmonton for this recognition, much appreciated. So I pass the podium, and I'll be happy to, if there is any question, to answer.
Thank you very much, Amir. Very detailed lecture. I have to confess that I didn't grasp every detail of your. Are there any questions from the audience? I don't have any on the chat. I mean, I think with the small number that we are, if you'd like to unmute yourself and ask a question, by all means do so. Give you a few seconds to think. Hi,
Amir, I have a question to get started. It's in the chat, but your semi-analytical model that you did, and I think you showed that the oil recovery dropped about 40%. I think that was slide 6, if you wanted to.
Yeah, just let me to bring it back. Yeah,
I was just wondering if you had any field data to try and validate those findings, or is that, what confidence do you have? Well, maybe not confidence, but yeah, were you able to ground those findings or results with some field data or any experimental data?
For the analytical one? Yeah. Here, actually, not any field data, but I conducted some experiments here. Oh, can you see the slides? No?
Not yet, no.
Okay.
No, you need to share your screen again, Amir.
Yeah. You can see that here, yeah? Yes?
Yeah.
Okay. Here, actually, I just tried to actually conduct some recovery experiments on Indiana limestone specimen. It's a core space experiment. And you can see that this is actually a normalized volume imbibed. It's a recovery. It's a recovery of the specimen. And by increasing the effective confining stress from 1 MPa here to 30 MPa, this is actually purely coming from the experiment. There is no, all these measurements, these are experimental data. And you can see that there is a huge, actually almost, this is 40%, and this is like 25% at 30 MP. It's a huge, almost the same, in the same range of drop in the recovery of the specimen by increasing the effective confining stress during the spontaneous imbibition. Yeah, and this is again the simulations coming from the pore scale studies, and it also confirms the same change. It means that not only in a continuum scale analytical models that I did in that study shows a huge drop in the recovery, but even pore scale simulations and the experimental data actually confirm that huge drop in the recovery of the specimen. But there is, I have no field data for this to confirm it in field scale. It's just the in core scale and micro scale.
Mm-hmm. Thanks, Amir.
No.
If no one else has another question, I have a bit of a follow-up one is how would industry use your model or your findings to aid in their operations and operating their wells and stuff?
Yeah, that's a very good question, Nick. This is actually, for example, in this slide, I were talking about here in this plot, I showed that the fracture, like capillary pressure change in a great way. Actually, it's a huge jump in the capillary pressure of the fracture by increasing the effective confining stress. This is something that is literally ignored in industry. In all simulation, they assume that fractures are in flow simulations, fractures are channels. And that's why the capillary pressure is always like this, the blue line. It's almost zero because it's a channel, phases can easily flow through that. And this huge change and upward shifts in the capillary pressure is ignored in many simulations for fracture reservoirs, for flowing fracture reservoirs. And it shows that if the industry want to include all these geomechanical interactions, they should actually reconsider their simulations methodologies, process, adding more stress-dependent properties, not only just porosity and absolute permeability. I showed that multiphase flow properties are also changing, but at the moment, none of the commercial flow simulation or reservoir simulation softwares are equipped with such an option to update the multiphase flow properties like relative permeability and capillary pressure with the stress. So that's why once we wanted to add these impacts, we needed to add a code and add these impacts sequentially into the codes like CMG, commercial software like CMG or Eclipse. These are things that should be added. And I believe that not only with my research, some others actually have shown similar interactions. So these should be added into the modeling, and of course for the decision making for the future, and planning, future planning for oil and gas industry, and also for CCS. For the moment, I'm working on Acquisto CCS project, and this is actually exactly the same process happening there, because once these properties are changing, it means that the reservoir allowed less CO2 to be stored inside the reservoir, or depending on the change in the stress. So these are things that we should add to our models and actually add them into our decision-making processes, I believe. Thank you.
Thank you, Amir.
Yeah.
Hossein, would you like to unmute yourself and ask the question?
Thanks, Amir, for the presentation. I think you already answered my question. My question was regarding whether you studied this change in relative permeability when there's a mixed gas and water phase for CO2 application or other application.
Yeah, actually my current research as a postdoc is exactly about CO2 and in brine reservoir, it's water and CO2, but the process is almost similar to like what is happening here, because this is nitrogen and water. And the only difference is CO2, especially once we are dealing with CCS projects at that pressure and temperature. For example, in case of Acquisto, CO2 is supercritical CO2. It turns into it's not liquid, it's not gas, something actually in the middle. It makes the problem even a little bit more complex, but yeah, the process is the same, and you need to consider these change in the multiphase flow properties into models for other applications like CO2 storage.
Great, thank you.
No, thank you very much.
Are there any other questions? Rick, I thought you'd probably have a really hard question for Amir, but give people a chance to think. Okay, well, if there are no further questions, I'd like to congratulate you, Amir, on your award. In normal circumstances, we would at this point want to hand you your certificate and get a round of applause, but maybe we can get a round of virtual applause from the audience, and we will get you a certificate as soon as circumstances will allow.
Thank you very much, Sean.
Okay, and thank you for an excellent lecture. I can't help thinking that there must be wider applications of this, and I'm sure I know you're focused on the oil industry, but and carbon capture and storage. But yeah, I think students of the future will be needing to absorb much of the knowledge that you're generating now. So thank you for the lecture. Our next event will be at the Geotechnical Society of Edmonton event, will be a 2-lecture series in January. And the topic of that will be 3-dimensional numerical analysis. The speaker will be Murray Fredland. Watch for notices from the GSE with dates and times, and we'll give you an overview of the content of the lectures as well. Lectures are planned to be 2 hours long, but we'll run them over lunchtime, and hopefully that'll make it easier for people to attend. So, and they will be in 2 different consecutive weeks. That's the current plan. So the information will come out to you in notices from the GSE, and it will also be posted on our website. And you all know our website address, geotechnical.ca. So on behalf of the GSE executive, if it's not too early to do so now, I'd like to wish you all a happy Christmas, a peaceful holiday, and a safe return to an improved normality in the new year. By the sound of it, with a bit more optimism than we've had of late. So thank you very much, and we'll see you at our next event, I hope.
Thank you very much.
Thank you.